In this example, we'll be finding exact circular function values. Find the exact values of sine 3 pi over 2, cosine 3 pi over 2, and tangent 3 pi over 2. First, let's sketch the unit circle. Labeling the fact that the radius is equal to 1, so this would be 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Now we're interested in sine of 3 pi over 2. Well, 3 pi over 2, of course, is this angle here, landing right on the y-axis, where we have an x value of 0 and a y value of negative 1. Since we know that sine is the corresponding y value, then the sine of 3 pi over 2 is negative 1. For the cosine of 3 pi over 2, we look for the corresponding x value, which is 0, so cosine 3 pi over 2 is 0. And for tangent of 3 pi over 2, it is equal to the y value divided by the x value, negative 1 divided by 0, so it is undefined. In this example, we'll be finding exact circular function values. Use the figure to find the exact values of cosine 7 pi over 4 and sine 7 pi over 4. So the figure that you have in your book, to which this problem refers, is this figure. What we want to do is look for the angle of 7 pi over 4, which would bring us all the way around to here. And therefore, it is this point here that we're interested in. That is the square root of 2 over 2, comma, negative the square root of 2 over 2. So let's write that point down. We have the square root of 2 divided by 2, comma, negative the square root of 2 divided by 2. Cosine 7 pi over 4 would be equal to the corresponding x value of this point. The corresponding x value, square root of 2 divided by 2. How about the sine of 7 pi over 4? That would be the y value of the corresponding point, and therefore it's equal to negative the square root of 2 divided by 2. Let's take a look at another evaluation. Use the figure and the definition of tangent to find the exact value of tangent of negative 5 pi over 3. So once again, here's the figure to which the problem refers. You'll find this figure in your book as well. We want to look for the angle negative 5 pi over 3. That will swing us all the way around to here. I can draw the terminal side, and it shows that we intersect at the point 1/2, comma, the square root of 3 over 2. So let's write that down on the next sheet. It's the point 1/2, comma, square root of 3 over 2. Now the tangent is equal to the y value divided by the x value of this corresponding point. So it would be the square root of 3 divided by 2, all of that divided by 1/2. To divide these fractions, we change it to multiplication by the reciprocal. So we have square root of 3 over 2 times 2 over 1. And therefore, when we simplify, the tangent of negative 5 pi over 3 is equal to the square root of 3. Let's do one more. Use reference angles and degree radian conversion to find the exact value of cosine 2 pi over 3. Let's begin by looking at converting 2 pi over 3 to its equivalent degree measure. We do that by multiplying by 180 divided by pi, giving us a result of 120 degrees. So the cosine of 2 pi divided by 3 is equal to the cosine of 120 degrees. 120 degrees is in quadrant 2. Cosine is negative. Reference angle is 60 degrees. So this is equal to negative the cosine of 60. Cosine of 60 is 1/2. It's equal to negative 1/2. So cosine 2 pi over 3 equals negative 1/2. In this example, we'll approximate circular function values. Find a calculator approximation for the circular function value cosine of 1.85 radians. So let's bring in our calculator. The first thing you want to do is to make sure that it's in radian mode. So we'll press the mode key. We'll move down to the third line where it says radian, and now that's where you see it blinking. I need to press the enter key so that it accepts that I want it now to be in radian measure. Once I have that blinking as it is, I can hit the second quit key, which brings me back to my screen where I press the cosine key here. That gives me cosine of, and now I enter 1.85. I close the parentheses, although that's not completely necessary, and then I press the enter key where I get the result negative 0.2755902468. And let's write down then that the cosine of 1.85 radians is equal to, and actually we'll approximate it to 4 decimal places, negative 0.2756. Let's work another calculator approximation. This time it's for the circular function value cosine of 0.5149. So let's bring in the calculator, and we will press the cosine key and then enter in the number 0.5149. This time I'm not going to press and close the parentheses, but simply hit enter. And I get my result of 0.87034199714, which will round off to 4 decimal places. So let's write that down, that the cosine of 0.5149 is equal to approximately 0.8703. All right, let's continue. We'll find another one. Find a calculator approximation for the circular function value cotangent of 1.3209. Now, of course, the calculator does not have a cotangent key, so we'll use the reciprocal identity and say that cotangent of 1.3209 is equal to 1 over the tangent of 1.3209. So here's what we're going to do. We'll bring the calculator in. We'll clear what's there. And now what we're interested in doing is first, we're going to press the tangent key. We'll enter in 1.3209. We'll press enter, which will give us a result of 3.9180, etc., as you can see there. But now here's the important thing. We'll come back, and what we want to do is press this key right here, the reciprocal key, which on the calculator looks like x to the negative 1. That is, it looks like this. Let me slide that in. X to the negative 1, this key. So I press that, then I press enter, and it gives me the result, 0.25523, et cetera, and we'll round that off to 4 decimal places. So now we'll say that the cotangent of 1.3209 is approximately equal to 0.2552. Let's do one more. We're going to, again, find a calculator approximation for the circular function value secant of negative 2.9234. Secant key is not on the calculator, so we'll use the reciprocal function 1 over cosine. And so this would be equal to 1 over the cosine of negative 2.9234. So we'll bring in the calculator, clear what's in there, and now what we want to do is press the cosine key, enter in the negative key, which is the key down here, not the subtraction key over here, but the negative key here, and type in 2.9234. I press enter, and it gives me the value, and negative 0.97629022718. And now I'll press the same x to the negative 1, which is the reciprocal key, and then I'll press enter, and the readout will display negative 1.024285532, which will round off to 4 decimal places. So let's write that down, that the secant of negative 2.9234 is approximately equal to negative 1.0243. In this example, we'll find a number given its circular function value. Approximate the value of s in the interval 0 to pi over 2 for cosine of s equals 0.9685. So this time we're given the value of the cosine, and we're asked to find the real number s whose cosine is that. That should make you think of inverse cosine function. We'll use the calculator to do that. What we'll do is say that s is equal to the cosine inverse of 0.9685. That's what we'll enter into the calculator. So let's do that. So what we want to do is press the second key, followed by the cosine, which is cosine inverse key, and now enter the number 0.9685. You can choose to or not close the parentheses, which I chose this time to do so. Now we press enter, and we get the result of 0.2516615,917, which will round off to 4 decimal places, and therefore s is equal to 0.2517, and actually approximately equal to 0.2517 radians. Let's do another one. Let's find the exact value of s in the interval pi to 3 pi over 2 if tangent s is equal to 1. So here we're given the tangent value, 1. We're asked to find the real number whose tangent is 1. That should make you think of inverse tangent. Now, the good thing is we know this one. It's one we're supposed to have memorized. We know that the tangent of pi over 4 is equal to 1. When we look at the interval they've asked us to find the angle in, we have that it's in quadrant 3. Tangent is positive in quadrant 3. So therefore, what we know is that the tangent, and now let's put the angle in quadrant number 3. So we'll have pi plus the pi over 4, the reference angle, added to the pi. And so that's equal to tangent of 5 pi over 4. And tangent of 5 pi over 4 is then also equal to 1, which is exactly what we were looking for. So S is equal to 5 pi divided by 4 radians. In this example, we'll be modeling the angle of elevation of the sun. The angle of elevation theta of the sun in the sky at any latitude L is calculated with the formula sine theta equals cosine of d times cosine of L times cosine omega plus sine of d times sine of L, where theta equals 0 corresponds to the sunrise, and theta equals pi over 2 occurs if the sun is directly overhead. Omega, the Greek letter omega, is the number of radians that Earth has rotated through since noon, when omega equals 0. D is the declination of the sun, which varies because Earth is tilted on its axis. Now we'll work an application using this formula. Sacramento, California has latitude L equals 38.5 degrees or 0.6720 radian. Find the angle of elevation theta of the sun at 3 p.m. on February 29, 2008, where at that time D was approximately negative 0.1425 and omega is approximately 0.7854. Let's begin by writing down the formula. Sine theta is equal to cosine of D times cosine of L times cosine omega plus sine of D times sine of L. And let's now substitute the values of D, negative 0.1425, L, 0.6720, omega, 0.7854. And we'll do the same here and here. So what we have is cosine of negative 0.1425 times the cosine of L, 0.6720, times the cosine of omega, 0.7854, plus, which I'll write on the next line down, plus sine of D, and that's sine of negative 0.1425, times the sine of L, which is 0.6720. The next thing we would do is evaluate each of these and simplify this expression. I need more room to do that, so we'll bring in a new sheet. I have done this on the calculator, which is, of course, where you will also do it, making sure that your calculator is in radian mode, and you'll find that the sine of theta is approximately equal to 0.4593426188. What we're interested in is, of course, theta. So we're going to use inverse sine. So on the calculator for theta, we're going to say that theta is equal to sine inverse of this number, 0.4593426188. Substituting that into the calculator, we have theta is approximately equal to 0.4773 radians, or if you changed it to degrees, 27.3 degrees. Suppose that angle TVU measures 60 degrees. Find the exact lengths of the segments OQ, PQ, VR, OV, OU, and US. Well, angle TVU is this angle right here. And that angle, we're being told, measures 60 degrees. Well, if we now look at angle OVR, that is a vertical angle with angle TVU, which means that angle is also 60 degrees. If we now look at the triangle OVR, it is a right triangle as signified by the right angle symbol here. And that means that this angle theta is the complement of this angle, which is 60 degrees, and therefore theta is 30 degrees. Now we can take that information and look at it on a larger diagram and then find the exact lengths of each of those segments. So here's our figure with our angle theta as 30 degrees. And then the next thing I want you to notice is we have the arc here of part of a unit circle because this point is labeled as 1, 0, and this point up here is labeled as 0, 1. What that tells us is that the length of the segment OP is 1. That's the hypotenuse of the triangle OPQ. Now what we can do is find the length of OQ, and OQ is the side adjacent to the 30-degree angle, and so we can use the fact that the cosine of 30 is equal to the side adjacent divided by the hypotenuse, which when you divide by 1 simply gives you the side OQ. So OQ is equal to the cosine of 30 degrees, which is one of the angles you memorize, the cosine of square root of 3 divided by 2. Next, we find PQ. PQ is this segment here. That segment is opposite 30 degrees, and we know the sine of 30 degrees is the side opposite divided by 1, so in this case, it's simply that side opposite, PQ, so PQ is equal to the sine of 30 degrees, and again, that's equal to 1/2. Next, we'll find the side VR. VR is this side here. That is equal to, or I should say the tangent of 30 is going to be equal to the side opposite, which is VR, divided by the side adjacent to it, which would be OR. We know that OR is, or the point R lands at 1, 0, which means the length of OR is equal to 1. So OR is 1. So therefore, VR is simply going to be equal to the tangent of 30 degrees because the side opposite divided by 1 is just the side opposite. So VR is equal to the tangent of 30 degrees. Again, an angle whose tangent we are to memorize, square root of 3 divided by 3. Next, we will find the length of the segment OV. OV is from here to there. So it's the length of this segment, which is the hypotenuse of the triangle OVR. Now, we just determined that VR is the square root of 3 divided by 3. When we want to find this OV, for example, we could use the secant of 30 degrees. And we can use the secant of 30 degrees because we know that the secant of 30 degrees is the hypotenuse divided by the side adjacent. And the side adjacent to that is 1. And so OV would simply be equal to the secant of 30 degrees. The secant of 30 degrees is equal to 2 square roots of 3 divided by 3. Next, let's find OU. To do that, we have to use a different triangle than we've used already. Let's take a look. We need to use triangle OSU, which is this triangle here. It's still a right triangle, as we can see the right angle symbol here. And what we know is that this point is 0, 1, and that means the length O to S is equal to 1. Also, because this line is parallel to this line, and this segment OU is a transversal that cuts two parallel lines, we can say that the angle up in here is equal to 30 degrees because it's an alternating interior angle with theta. So now what we see is we have this triangle here where we know 30 degrees is this angle, this side is 1. We're looking to find from O to U, which is the hypotenuse of this triangle. So we have the hypotenuse, the side that is opposite angle 30 degrees. So we want to use cosecant because cosecant of 30 is the hypotenuse divided by the side opposite, which is 1, and therefore cosecant of 30 is simply equal to the length of OU. So this equals cosecant 30 degrees, which is 2. And finally, we want to find the length for US, and US is the length from here to there. And that is still part of this larger triangle in which we have the 30-degree angle, and we have the 1, but we also now have the hypotenuse is equal to 2. So let me write a 2 here, showing that that length is 2. Now we can use the cotangent of 30 to find this length, US, because the cotangent of 30 is the side adjacent, which is US, divided by the side opposite, which is 1. And so US divided by 1 would be US, so US is the cotangent of 30 degrees. And that's equal to the square root of 3. So we've now found each of those line segments exactly.